Hi, we're a group called the Engineering Cheeseheads, and we're working on this project as a part of the Intro to Engineering 170 course at the University of Wisconsin-Madison. This project is for the Engineering Without Borders team, which is also based in the UW, who are working on a drinking water system for the people of the Pericon-Chuacaral Sector Dos region in Guatemala. We've been tasked with researching, formulating, and testing a plan for a water treatment system. Our final work is being proposed as a part of the overall system that will be installed by the Engineering Without Borders team.
We have a $5,000 budget for our system that needs to disinfect and filter water at a rate of 70 gallons per minute. It will be run twice a day for 2 hours each, regardless of clean water consumption. Our design will need to be made using locally sourced materials to minimize cost and difficulty of repairs and maintenance. Our design will also need to operate safely in a humid environment with no risks for local wildlife or communities. Energy is not an abundant supply in Guatemala, so our design needs to have minimal power requirements.
Our first design alternative was a double chlorination system, which is a system that we chose as our final design. This design uses chlorine pellets and micron filters, which is discussed further in this presentation. Alternative 2 was a reverse osmosis system with chlorine pellets, but this design alternative was much too pricey. Design 3 was based on UV light exposure and would also need a filtration system with a membrane filter. The UV filters would be very hard to replace, making the alternative 3 impractical.
To determine the best overall system, our team created this decision matrix based on 7 criteria ranked by importance. The effectiveness of disinfection and filtration were the most important, as it was our overall goal to improve water quality. The system also needed to have easy repairability, as it would be useless without functioning properly. Our next constraints included the limited time and costs we had for our system to operate. And last on our list was safety, regarding any hazards during maintenance, but this wasn't very apparent in our chosen systems. As our team judged each design based on these criteria, it was scored and determined that the double chlorination system would be best suited for our community.
Once the water filter was chosen as the primary object to be designed by the team, each member was given a component to design on their desired CAD software, such as SolidWorks or Autodesk Inventor. As each piece was completed, it was added to an overall assembly on Autodesk Inventor, and then once the assembly was completed, it was transformed into an exploded view. Each component was designed to either A, be 3D printed, such as the filter housing, the cap, the spanner wrench, and the bracket, or B, each component could be purchased. This would include the filter, the screws, and the O-ring.
After fabrication comes the testing of the products. Our first test analyzes the bacteria and flow rate. The goal of this test is to be able to identify how much bacteria is actually being filtered out by our filter and the filter body, as well as what the max flow rate of our system can be. The second test is to find out which filter pore size would best suit our needs. In this test, we simply use different micron-sized membranes to test which membrane filters out the most debris and bacteria while maintaining our flow rate calculated in test 1. Our final test revolves around the spanner wrench. We are testing the fitting as well as the strength of the spanner wrench to ensure proper dimensioning and fabrication of the wrench.
The process of solving the problems set forth was not an easy one, and challenged our group to do things many of us had never done, like CAD drawing and making a design matrix. We hope that our project will contribute to water treatment in Caserío El Pericon, Chuacaral Sector 2 in Guatemala, as we have found a solution to water treatment that is cost-effective, efficient, and safe. Thank you. We would like to acknowledge Professor Harrington, other student assistants, Claire and Riley, for being supportive and helpful during the entirety of this project. We would also kindly like to acknowledge EWB for taking time out of their day to listen to our midterm presentations and providing us with this project opportunity and experience.